This video is going to cover the first section of our next unit, which is on ratios. And the reason why I put a pun in about fractions is because when you understand ratios effectively, you will know that ratios and fractions are just the same thing. Even though we talk about them sometimes in different ways, their goal is to represent the same numbers. So for example, if we're looking at these three numbers, or ratios, we should be able to convert them into three different forms, and for those forms to all be the same if we're looking across. So if I have the ratio 3 to 4, that means 3 of something to 4 of something else. If I wanted to write that in a different form, I can write in 3:4, which means the same thing, 3 to 4, 3 to 4. Now, the one that I like the most is fraction form, which is just the same, 3 to 4. If you remember, when we work with fractions, we can say these a lot of different ways. We can say these 3/4, 3/4, 3 divided by 4, and now we can also say 3 to 4, and they're still going to mean the same thing. If I go down here and look at the ratio 2 to 8, I can write that in word form, 2 to 8, just like that, means the same thing. I also can write it in the fraction form, 2/8 or 2 to 8, and of course I can simplify that fraction to be 1 to 4. So when we're thinking about ratios, I'm hoping this first video feels kind of familiar and that it's very similar to what we've been doing in the past. And that is all ratios are. Now, as we get to ratios, it does get a little bit reading intensive. In the top here, we've got 4 black circles and 3 light orange rectangles. And when we're doing ratios, there are a ton of options on what we can do with those. So we have to make sure to read very carefully. When you're reading the ratio, I want you to always be keying for the word 2. That's going to tell you what is being compared to what other value. So if I have the ratio of orange rectangles to black circles, that means the top of my fraction would be 1, 2, 3 orange rectangles, and the denominator of my fraction would be 1, 2, 3, 4 black circles. Now I can write that as 3 to 4, 3 to 4, or of course 3 to 4. All of those are acceptable, and it just depends on what you're trying to do with that problem on which form is going to be most correct. For the rest of this video, I'm going to choose one of those 3 forms, and I'm going to rotate between them. Purely for me, though, I'm going to choose the fraction option most often. That's quite the tongue twister, because I think the fraction option is going to be most realistic. So down here, the ratio of black to total shapes. Okay, so there are 1, 2, 3, 4 black circles, and there are 5, 6, 7 total shapes. So that's 4 to 7 as our ratio. And on the right, ratio of orange rectangles to total again. Well, this time it's going to be 1, 2, 3 to 7 total. Very, very important that you read carefully on the directions when we're working with ratios, because these 3 ratios all look different, but they represent the same information. It just depends on what you're being asked for. When you're dealing with a large number of options or shapes, what I like to do is count up the total right away. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I know before we do any of the work below that there are 12 total shapes here. So first one says ratio of red to green. Once again, we're going to identify the important keyword here. So let's find how many red shapes there are. 1, 2, 3, 4, 5. And there are 1, 2, 3, 4 green shapes. So 5 to 4 in this example. Down here, where it gets a little bit trickier, it says ratio of green and blue to total. So this time, it's green and blue as the numerator of our fraction, and then total as the denominator. So we know there are 4 green, and there are 1, 2, 3 blue, for a total of 7 objects. And the total number of shapes altogether is 12. So that's 7 green and blue to 12 total objects. Then ratio of blue to total, 1, 2, 3. And we know from up here there are 12 total. Now what is important here is that this ratio, 3 to 12, is correct, but we could also simplify to get the fraction 1/4. And it simply depends on if it's asking for the fraction to be in simplest terms. So 3/12 or 1/4. The bottom one is definitely the trickiest, and IXL is going to throw in a couple of these options every once in a while, and you have to read it very carefully. The ratio of shapes to total objects. So, of these 12 objects, all 12 of them are shapes, and there are 12 objects total, which is a ratio of 12 to 12, which can be simplified down into 1 to 1 or 1 to 1. Got to be very cautious about that. There's going to be a couple IXL problems if you pick that option where it's going to feel like they were trying to trick you. So make sure you read very carefully. Now, we've covered equivalent fractions, but if we remember that the word equivalent means equal, when we see equal ratios, we are actually thinking of equal fractions. So when we were working on the next few slides, what we're really trying to do is find equivalent ratios which are equal fractions. So if you're ever given a ratio like this, 3 to 4, what I would recommend is turning it into a fraction 3 to 4 right away. And on this page, we're going to ask us to do 2 equal fractions. So 3/4, what I could do is I could multiply the numerator and denominator by the same number. And I'm going to pick the number 2 just because that's the smallest option that will give me a different fraction with whole number numerator and denominator. 3 times 2 equals 6. 4 times 2 equals 8. And I'm hoping that some of us are realizing, hey, we've already done this. And that's really good, because the best part about math is that you learn the same strategies over and over and over, and you just apply them in different ways. I could do that process again to get 12/16. But if you remember fractions, there's an infinite number of equivalent fractions that we could use, and it just depends on which strategy you're using to try to make them. So if I'm doing 5/6, I could multiply the numerator and denominator by 3 to get 15/18. I could also multiply the numerator and denominator by 4 to get 20/24. And those would all be fine. And if you didn't pick the same fractions that I did, that's great, because there, like I said before, there are an infinite number of options. Now, if we are doing equivalent ratios, what we need to figure out is what number is going to be in the numerator or denominator of the other equivalent fractions. So what we have here is we have the ratio 3/4, and we need to figure out if it is something over 12 that's equivalent. So the way that we think of this one is we realize that this number times something is going to equal that number, and this number times the same thing is going to equal that one. So I can think from the left to the right or the right to the left, and I want to figure out what pattern is happening to get that number. Well, I know that 4 times 3 is equal to 12. Therefore, 3 times 3 has to be equal to the numerator of this fraction, which should be 9. And that does make sense because 3/4 is the same thing as 9/12. Now down here on the bottom, sometimes it's going to be written as a variable, which in this case our variable is x. And the word variable means change. So the reason why variables like x, y, a, c, or any letter are called variables is because they can represent any number, and that number can always change. So if you thought of the box at the top portion and you realize that makes sense, but then you look down at the x in the bottom one and think, I don't really understand what they're doing, you can always erase it and think of it as an empty box. So all we have to do then is say x equals. Whatever this box is our x value. So same thing as before. We have to figure out the pattern, this time once again from left to right. Well, 7 times 4 is equal to 28. Therefore, 5 times 4 will be equal to 20. And then x has to equal 20.